Hi, my name is Margret. In this program along exercise, we're going to write some JUnit tests together. Let's start by creating a class called TreasureChest. I prepared already a Java project, and now I'm going to add a new package in my source folder. This new package is going to be called unit testing. Here it is. And I'm going to add a class inside my package. And this class is TreasureChest. Let's take a moment to have a look at the UML class diagram together. You can see there are 3 fields. 2 of them are underlined. In the context of a UML class diagram, underlined means static. One of them is in all caps. That means it is a static constant. The amount of gold per coin never changes. However, the gold price can change. As a matter of fact, it updates or changes quite frequently. But it is totally independent of the treasure chests. And if we have 5 treasure chests, the value of those treasure chests all depends on the current gold price. The amount of gold in each treasure chest, that is specific to the individual treasure chest. That is an instance field. We also have a constructor, we have a getter, so we can look how much gold is in my current treasure chest. We can't just set a new amount, but we can add and remove gold. We can also look what is the current gold price, and we can set that. We can change it depending on the market. The gold price changes and we can update that. We can also calculate the value of my treasure chest in dollars, and there's a toString method that returns a string representation of our treasure chest. What I would like you to do is the following. I would like you to implement all the information from this UML class diagram into Java. Every time there is a return type, for example integer or big decimal or string, just return the default value. Don't implement it yet because I haven't given you the information about the implementation details yet. You can auto-generate the getters because they just do the getter typical information, which is returning the field value. One other thing I want to point out is big decimal. Every time we deal with money, we should use big decimal because double is not precise enough. And the default value is null. Take the time to translate the information from this UML class diagram into Java. Pause the video. When you're done, press continue. Here is something to compare with. I took the information from the UML class diagram and translated it into Java. Notice how I started the doc comments. Even though I haven't provided the full information yet, we do know that we need doc comments and there are certain parameters and return values. Also note that I commented out the constant, gold per coin. Constants have to be initialized right away, and I haven't provided the value yet. Now I'm going to scroll down. Another thing I would like to point out is the comments to do. This is my own reminder that I just temporarily returned the default value to make my code compile, but I still have to revisit those methods and make sure to return the appropriate values. Different on my getter, the getter does not have a to-do comment because it returns already the proper field value. At this point, I'm going to provide some additional information, and I'm going to do that by writing it directly in the doc comments. Let's start with a look at the class. This is a treasure chest that is defined by the amount of gold coins that are stored in it. In this class, we assume that each coin is a $20 Liberty Gold coin. This assumption, combined with the knowledge of the gold price and the amount of gold in each coin, allows us to calculate the dollar value of the treasure chest. Here is how a $20 Liberty Gold coin looks like, and you can read in the specification each of them contains 0.9675 ounces of gold. And this is the value I used right here for our constant, that never changes. Even though the gold price fluctuates, the amount of gold per coin is constant. Notice I had to create a new big decimal because we created it as a big decimal. Doing so has an advantage when we need to use it in a calculation in combination with our gold price. So using the big decimal also for the gold per coin prevents us from having to convert the type every single time. Notice also that I used doc comments for my fields. The reason is the following: if I would have used an inline comment, my lines would have been too long, and so I thought this might be one of the situations where it's a nice opportunity to introduce doc comments that can be used for fields. So here, this gold means it's the number of gold coins in the treasure chest. The gold per coin is the amount of gold per coin measured in ounces, and my gold price, that's the price of an ounce of gold. So we provide that additional information also when we initialize our gold in the treasure chest. You might have already assigned the gold coins to your gold. However, now I provide some additional information. I tell you that there should be an illegal argument exception if gold coins is negative. So we can create an empty gold treasure chest. We can create a treasure chest with a certain number of gold coins, but there cannot be -3 gold coins in our treasure chest. So we want to make sure we have this illegal argument exception. That's how I like to start my constructor. And we are going to check, well, if gold coins is less than 0, that means negative, then we are going to throw a new illegal argument exception, and we are going to provide a message for the user. The number of gold coins in a treasure chest can't be negative. At this point, we have a good start of class treasure chest. Most of the methods still return the default value, but that is okay. We declare the method signatures, and that is all we need to get started with the JUnit tests. Here is my Package Explorer. In your Package Explorer, go to your Java project, right-click, and we're going to add a new source folder. This is a best practice to separate the test code from your source code. On bigger projects, you might have a separate test project, but for the very least, you want to have a separate source folder. Notice there's also a folder. That's the wrong one. We need a source folder. And my source folder is going to be called test, because we're going to have the test code in the test folder and the source code in the source folder. Now at this point, I go back to my class TreasureChest.java. I right click and I create a new JUnit test case. When I do that, it gives me different options. JUnit 3 and 4 are really old, so we are going to use the JUnit Jupiter test. We want to use the test source folder. So I have to change that up here. Notice the name is treasure chest with the suffix test. That makes it easy to relate the test cases to your source code. Here are a number of checkboxes. Sometimes we call it fixture because they provide a fixed environment against which we're testing. Setup is executed before every test. Setup before class is only executed once, then we run all the tests in that class. Similar with teardown. I give you an example. Let's say you are going to test some functionality related to a database, adding, deleting, removing data sets in a database. So every time I add, remove, delete, I want to make sure I start with the same records in my table. Otherwise, I can't predict the outcome. So in my setup, I ensure that the table is always filled with the same records before I start every single test. However, once when I start my tests, I build up a connection to the database. And after all my tests are finished, then I tear down my database connection in the tear down after class method. Typically, we know when we have one bigger task that has to be done once before all my tests, like creating a database connection and tearing it down again. It's not always that easy to see whether we need a setup. I recommend, if you're in doubt, check it, because you can always delete that one method. A little easier to delete the method than to create it if it is not there. There is a big blue button, finish. Don't click it. It's a temptation, but there's an advantage if we use the next button first. When I check next, Eclipse allows me to choose what would I like to test. It gives me all kinds of methods and a constructor from my TreasureChest, but also all kinds of methods from class object. Now, class object, the root of inheritance in Java, has been very well tested. I'm not going to write any tests for class object. So I want to have all my methods and constructor tested from class TreasureChest and nothing from object. Now I'm ready to press finish. At this point, Eclipse detects that the JUnit5 library is not on the build path, and it offers to add it. And so we say, yeah, let's get it done. But the moment I press OK, all those red wiggly lines appear. Let's roll over them to see what we can do about it. It tells me add requires org JUnit Jupiter API to module info Java. Let's do it. So let's see what happens here. I'm going to my module info Java. It added requires org JUnit Jupiter API, but there is yet another red wiggly line. Let's roll over that one too. And now it says move the class path entry JUnit5 to the module path. At this point, we have compiling JUnit tests. I'm going to open them, and you can see Eclipse created a nice starter class for us. At the top, we have some import statements. Here is a static import for class assertion. This one is very important because every JUnit test uses an assertion. That's how the JUnit test compares the actual value with the expected value. We also have imports for test and before each. The annotation test indicates that the method is a JUnit test, and the annotation before each indicates that we have a fixture. This method setup is going to be executed every time before a JUnit test is run. Notice that Eclipse created a JUnit test for each of the checkboxes we selected. Let's run the tests. You can see we had 8 tests that were run, 0 errors, and 8 failures. An error would be, for example, an exception. A failure is a failure in my assertion. So here I can see a list of the 8 tests, and all of them have a blue icon with the X. That means those tests failed. Also notice the red bar that indicates that we are not done testing yet. One thing I want to point out is the statement fail. So each of those tests calls a method fail, and the method says not yet implemented. That's exactly the message we get when we wonder why those tests fail. All of them tell me they are not yet implemented. Let's just say we would delete one of those methods. Let's see what happens. I'm going to run it again. And at this point, I still run 8 tests, but only 7 fail. Look at this one. Here is test addGold. It has a green check. That means it passed. Notice, a JUnit test passes by default. It always passes unless it fails an assertion. This is important. we need to make sure that we write meaningful implementation so we don't trick ourselves. We don't want to create an appearance that a test passed if we were really doing absolutely nothing. So it is a good practice to leave the fail method there until we're ready to replace it with some meaningful testing. Also notice that the bar is still 100% red. There's no indication in my bar that part of the tests, in my case one test, passed. I can only see that here. So the bar indicates not all tests have passed yet. If I have 1000 tests, a single one fails, my bar is still 100% red. Soon we're going to be ready to start implementing the first test. Which test should we implement first? Would it even matter? Should we just go top to bottom? We should start with tests that have the least or no dependence. I'll give you an example. If I test toString, all I need is my instance, and then my instance provides a string, I can test the string. However, if I test addGold, my addGold method is changing the field, and the only way I can find out whether my field changed is by calling another method, maybe a getter, maybe a toString method. So it depends on another method. And because it depends on another method, that other method really needs to work. So it should be tested first. There's a rule of thumb. We should test every public method. We should also test constructors. However, there is an exception. Sometimes we have auto-implemented methods. You see this, for example, when we implement getters like getGold. So we didn't write this code. This code was written by Eclipse, and we don't need to test that either. So I'm going to delete that. There's another getter. We have test getGoldPrice. That is also a boilerplate auto-generated getter that only returns the field. We don't need that either. So at this point, if I run it again, I will see that we have only 6 tests. All of them failed. Whenever we implement a test, there are certain rules and guidelines. We talked about one before, but we should start implementing the tests that are least dependent on other tests. There's another one. Whenever you test a method, you need to call the method in your test. This is important. So if I want to test the toString method, I need to call the toString method. And since it is an instance method, I need an instance. So I could create an instance of TreasureChest in each of the tests that tests an instance method. However, I could also create a field. That makes my tests more simple, easier to read. And so I'm going to create here a private field, TreasureChest, and I just call it treasure. I could assign a new TreasureChest to my treasure right as I declare it. However, since I am changing my TreasureChest, I'm adding, I'm removing, I need to ensure that there's always the exact same amount of coins in my treasure. Otherwise, I cannot accurately predict what should happen if I remove 1 or if I add 5. So I am going to initialize treasure in my setup method. By doing so, I ensure that every time we run a test, there is a brand new treasure with the exact same amount of coins. So in my case, I'm going to create a new treasure chest with 10 coins. I can use that treasure now confidently in my toString method. When we write a test, we need to know what is the expected value, what is the actual value, and does the actual value match the expected value. So here I'm going to create a couple of different steps. We're going to simplify that in upcoming tests, but just for the beginning, I want to spell it out to make it more clear and easier to see the pattern. In our case, we have a method, toString, that returns a string, so the expected value is of type string. And now I need to know what is my expected value anyhow. And we looked at that before in the doc comment. We want to have those brackets, the amount of gold, and then coins. So what I expect is that it would say we have 10 coins. That is my expected value. Now let's see what is the actual value. In order to find out the actual value, I need to call the method toString. Now I know the expected value, I know the actual value. Now we need to compare. In traditional testing, it would be the software developer or the tester who does the comparison. In automated testing, this happens automatically. That's where the assertions come in. So now I need to use an assertion to compare expected and actual value. I assert that the expected value and the actual value are both equal. Let's add a semicolon here. And at this point, I do have a finished JUnit test. Let's run it. Now, if I look at my toString method, I can see the test fails. And if I check why did it fail, let's just see here, it tells me the expected value was bracket 10 coins bracket, but the actual value was null. Not super surprising because we haven't implemented the method yet. At this point, give yourself a moment, implement the toString method. When you're done, press continue. So here is something to compare it with. We have a bracket, the number of gold pieces in my treasure, and then coins, space, another bracket. Let's see what happens when we run our test again. So here I'm going to run it. And this time the test toString is green. So we can see it passed the test because the expected value was the actual value. Let's have another look at things to consider when writing JUnit tests. I added creating one or more test instances as private fields because that often makes the code more simple and more clear. We also talked about 3 things we need when we write a JUnit test. We need an expected value, we need an actual value, and we need an assertion that determines whether the actual value matches the expected value. There is one more thing I would like to add. We should choose a naming convention for our tests and use it consistently. There are a number of frequently used naming conventions. In this video, I'm going to use the following. We are going to use the method name and underscore, then the state under test and underscore, and the expected behavior. Let's see how this applies to our toString method. The method name is toString. The state under test is we have a treasure chest with a positive number of coins, and the expected behavior is that it returns the number coins in brackets. So let's go back to our code and let's update the name. We start with the name toString and underscore. Now the state is positive number of coins, and then followed by the behavior. We return number coins in bracket. Now notice, number coins in bracket is not precise. It doesn't say bracket followed by a space, followed by the number, followed by another space. And the reason is we try to balance being descriptive with being concise. The overall goal is we want to be helpful. We want to catch bugs in our code. That is what the unit test should do for us. And the exact description of the format that is specified can be found in the doc comment. So here I have one single test for my toString method. Typically, one single test is not enough. If I just test for one situation, in our case for 10 coins, that could have been a hard-coded return string. So I want to have a second test that once again tests my toString method, but with a different value. Now I have to decide what should my state be that I'm testing for. And here I was testing for 10. I could say, well, I'm testing for 11. If I test for 11 coins, I could rule out that somebody returns a hard-coded string with 10. However, 10 coins, 11 coins, 12 coins are all treated the same. One number that would be different is 0. What happens if there's nothing in my treasure chest? What is the expected output? Do I still write 0 coins? Would I just have the empty brackets with nothing in between? We know what is expected because we have seen the doc comments, but there is more than one possible solution of creating a meaningful string for a empty treasure chest. Here we have a toString method and we say no coins as our state, and we return 0 coins in brackets. My expected value is 0 coins, but treasure is not going to help us in this situation. If I want to test with no coins, I need to create a second treasure chest. If I am convinced I'm going to use it only once, I could create a treasure chest right here inside my test method. However, an empty treasure chest might come in handy in other situations as well. So I'm going to add a second field. Private treasure chest. Let's call it empty chest. Again, I'm going to initialize it in my setup method. So here I have my empty chest. And I'm going to assign a new treasure chest. And this time it has 0 gold coins inside. Now that I have an empty chest, I can use that in my second test with no coins. So I say expected is 0 coins and the actual value is the following. I use my empty chest toString and then I compare the expected value with the actual value. Let's save and run the program. And you can see we have a toString method with positive numbers of coins and a toString method with no coins, and both of them passed. We tested for positive numbers, we tested for 0. Now the question is, should we test for negative numbers? And the answer in our case is no. The answer is no because our constructor ensured that we never have a negative number. If the user tries to create a treasure chest with a negative number, then it will not be created. Instead, an illegal argument exception will be thrown. Now we might wonder, how can we be so sure that the constructor works as expected? And that is a reminder, we need to test the constructor. This is something that should be tested early because we always call the instance methods on an object and we always use a constructor to create the object. So it's really important that the constructor works as expected. Here is the test for my constructor. I'm going to adapt the name to fit our naming convention. We start with the name, followed with the state. We say the state is a positive number of coins, and that is followed by the behavior. When I pass a positive number of coins, I expect all coins to be stored in a treasure chest. So at this point, I'm going to call the constructor because we're testing the constructor, so I want to make sure we call it. And I'm going to create a treasure chest with 7 gold coins. Call it treasure 7, and I'm going to assign a new treasure chest, and I'm going to pass 7 as the argument. So here I have a treasure 7. This is my treasure chest with 7 gold coins. My expectation is that now there are 7 coins stored in my treasure chest, or in other words, the field gold should have the value 7. I'm going to have an expected value. The getter, getGold, is returning an integer. Let's just double check that here. GetGold returns an integer because gold is of type integer. So my expected value also needs to be of type integer. And I expect gold to be 7. Now the actual value, that is going to be calculated by calling the getter. So I say treasure 7 and get gold. Now we are going to use an assertion to see whether the actual value matches the expected value. So here we are, and I'm going to save, and we're going to run. And when I look at my result, I can see there's my treasure chest, positive number of coins. That worked great. I'm also going to use a second test for my constructor. I want to make sure that the constructor also works correctly when we pass 0. In our case, 0 is allowed. We can create a treasure chest that is empty. So here I say my name is TreasureChest underscore. The state is 0 coins. And my expectation is that no coins are stored in the treasure chest. And now I'm going to create a treasure 0. I'm expecting that the value of the field gold is 0. Let's run the tests again. And I can see we have one test of my constructor with positive number of coins and a second one with 0 coins. I was writing 2 tests, both of them passed. Now I want to have a third one. I want to ensure that a negative number triggers the expected exception. So here I have my treasure chest. This time I have a negative number of coins. And the expected behavior is that it throws an illegal argument exception. JUnit5 has a method called assertThrows. It allows us to check that an exception of a specified type is thrown. So let's call assertThrows. This method needs an import statement. So I'm rolling over it. There's a static import of assertions. And now we need to provide the type of the exception that we expect. In our case, this is the illegal argument exception. And we need an executable. So for that, we're going to use a lambda-expression. And we're going to have nothing that goes to the call of our constructor. So here we're going to create a new treasure chest, and let's say with -2 gold coins. At this point I'm going to save and I'm going to run. And you can see here we have now 3 tests that test our constructor. One with negative numbers, it passed, it was throwing the appropriate exception. One that tests with positive numbers, and one that tests with 0. Before I move on, I want to spend a moment to explain what is going on in line 36 when I call assertThrows. The method assertThrows has 2 arguments. The first one requires a runtime class. We are providing a class literal, illegal argument exception.class. This is the argument that specifies which exception we expect. If I would expect a null pointer exception, I would have passed null pointer exception.class. the second argument is an executable. We use a lambda expression as our executable. Here we can see the parenthesis. That is the parameter list, which means we have no parameter, no argument, and the moment assert throws is executed, nothing is required in order to execute that method body. That method body has exactly one single statement, which is a new constructor call where we pass -2. Typically, we don't call a constructor without assigning it to a variable. We could do that. I could assign the TreasureChest -2 to a new variable called myTreasureChest. However, this myTreasureChest variable is never used. So when I roll over it, I'm reminded the value of the local variable is not used, which means we should not create variables that are not used. Would it work? Yes, it would. I could run my tests. It would still pass, but it is better code not to declare a variable, knowing that it will never be used. So, as a summary, when I call assert throws to test for an exception, I pass the type of the exception .class, and then on the right hand side I have nothing goes to a method body, and within the method body there is the code statement that is supposed to trigger the exception. In our case, calling a new constructor with a negative value. At this point, I demonstrated how to write JUnit tests for the method toString and for the constructor. I also showed you how you can test for specific exceptions. Now it is your turn. I want you to write JUnit tests for the method addGold. But in order to do that, you need to know what exactly is the method addGold supposed to do. So let's check the doc comment. Here it is. It tells me the method addGold adds the specified number of coins to the treasure chest, and it throws an illegal argument exception if the number of coins is negative. Give yourself some time, write some JUnit tests, and when you are done, press continue. I was creating 3 tests for my addGold method. In the first one, I was considering the situation that we are adding a positive number of coins. In that case, I expect that it increases the number of coins in the treasure chest. In the second one, I was considering the situation when we are adding 0 coins. In that case, I expect that it leaves the number of coins in the treasure chest unchanged. And in the third one, I was testing the situation where we are adding a negative number of coins. In that situation, I expect that it throws an illegal argument exception. Notice how in each of those methods I can rely that the treasure has 10 coins before I make any changes. So here when I add 5 coins to my treasure, I expect that it has 15 afterwards. When I add 0 coins, I expect that there's still 10 coins in my treasure. In my third test, I was using the assert throws method. I was clarifying that I expect an illegal argument exception, and I was calling the addGold method with a negative argument on my treasure, expecting that this statement right here is going to throw the illegal argument exception. Let's run the tests. When I look for my add method, I can see adding 0 coins passed, adding a positive number failed, adding a negative number failed. So I'm going to my positive number, I'm clicking on that. I say, why did it fail? So I'm looking into it, and it tells me it expected 15, but it was 10. let's check what happens in our addGold method. And when I go to addGold, I can see this method has not been implemented. The number of gold in my treasure chest always remains the same. Implement the addGold method. Give yourself a moment, pause the video. When you're done, press continue. Here is something to compare it with. I start by checking whether the input is valid. So if my number of coins is negative, I throw an illegal argument exception. Important, I also provide some information for the user. You might have different words, but it should give the user a nice feedback. Why did we throw an exception? What was the wrong part about the input? And here I tell the number of gold coins added to a treasure chest can't be negative. If we are still inside the method, which means the number of coins was not negative, it was 0 positive, then I am going to add the number of coins to my field gold. I'm going to save, go back to my treasure chest test and run again. And you can see that all 3 test methods from addGold passed. 1, 2, 3. At this point, you see already the proliferation of test methods. I started by creating separate variables for the expected and the actual value. That can be helpful when you're new to JUnit testing. However, there's room to simplify. So I'm going to use this method here. We are calling the addGold method, but rather than creating 2 separate variables, we are using the value directly as an argument for the assert equals method. So first expected, we're expecting 10, and then actual value. The actual value is provided by the getGold method. So I'm going to provide the actual value, and we no longer need those individual variables. You can see if you have really many test methods, it helps if we can keep them simple and clear. At this point, we tested the toString method, the addGold method, and the constructor. We are not done testing though. One of the methods that still needs to be tested is removeGold. In order to write those tests, we need to know what is the expected behavior of this method. We can find that out by looking at the doc comment. So here I have the method removeGold. It removes the specified number of coins from this treasure chest, and it throws an illegal argument exception if the number of coins is negative or if the number of coins exceeds the number of gold coins in this treasure chest. Now we know what it should do. Next step is we have to decide what are the different cases that need to be tested, and we need to write tests for each of them. Pause the video, write the tests. When you're done, press continue. Here is something to compare it with. I created 5 tests for the method removeGold. Removing some of the available coins reduces the number of coins in a treasure chest. Removing all available coins empties the treasure chest. Removing 0 coins leaves the number of coins in a treasure chest unchanged. Removing more coins than available throws an illegal argument exception, and removing negative number of coins throws an illegal argument exception. Let's run the tests. So here we are, and again the tests fail. We know already why the tests fail. We have not implemented the method yet. However, before we start implementing removeGold, I want to point out how important it is to provide the arguments of assert equals in the correct order. Sometimes there's the misconception that we could provide the arguments in any order because we're testing for equality, and if A equals B, B equals A. However, in the context of JUnit, the order of the arguments in assert equals is significant. it affects the feedback if a test fails. Let's take a moment and try what happens if we switch those two arguments. So I provide the actual value first and then the expected value. I'm going to run the test. And here you can see it. It failed. When I click on it, it tells me that there was an error. We had a failed assertion. We had an expected value, which was 10, but we had an actual value that happened to be 8. That is not correct. We did not expect 10. We expected 8 because we removed 2 gold coins, and we did not have 8 gold coins left. As a matter of fact, we had 10 left. We never changed anything. We didn't implement the method yet. So this feedback is not only wrong, it is misleading. Because of that, it is really important that we always provide the expected value first, followed by the actual value. Now that being said, please go to class TreasureChest and implement the method removeGold. Make sure to carefully read the doc comments so you have the proper implementation. Pause the video. When you're done, press continue. Here is something to compare with. This time I had 2 conditions. I used the OR operator because either one of them should trigger the illegal argument exception. I also provided a message so the user knows why the argument that was passed is considered unacceptable. Now, as soon as we ensured that number of coins is a valid argument, we are using it to decrease the amount of coins in our treasure chest. And at the end, we're returning the amount of gold that is left in the treasure chest. That was specified right here when it says it should return the number of gold coins left in the treasure chest. Some of you might have noticed that we wrote tests to check for the proper exception. We wrote tests to ensure that the field gold is updated correctly, but we have not written any tests to check whether the right value is returned. It happens quite frequently that we have JUnit tests and later on we discover that they are not as complete as we would like them to be. Whenever you discover a case that should be tested but doesn't have any JUnit tests yet, just go back to the file and add them. So that's what I ask you to do. Please go back to the TreasureChest test file and add unit tests that test for the correct return value. You will need more than one test. Give yourself a moment, pause the video. When you're ready, press continue. Here is something to compare with. I added 3 more test methods for removeGold. Removing some of the available coins returns the reduced number of coins in the treasure chest. Removing all available coins returns 0, and removing 0 coins returns unchanged number of coins in the treasure chest. So notice this time I was calling the removeGold method directly as a second argument of the assert equals method, because we are interested in the actual value, which is the value that is returned by the method call removeGold. I'm going to run the test. And all of the tests for class removeGold passed. We still have 2 more methods that need to be tested. Let's look at the method setGoldPrice. This is a static method. Still we can test it with JUnit tests. The main difference is that we don't call the method on an instance. Instead, we call it on the type itself. Let's look at the description in the doc comment. setGoldPrice updates the price of the gold with the gold price provided. However, there is an illegal argument exception if the gold price is negative. Create some JUnit tests for setGoldPrice. Pause the video. When you're done, press continue. Here is something to compare with. I created 3 tests for the method setGoldPrice. Setting a positive value updates the gold price. Setting 0 also updates the gold price, but setting a negative value throws an illegal argument exception. Notice every time I need to create a new big decimal, I need to use the new keyword and the constructor, because big decimal is a object, or sometimes I can use a constant. So big decimal provides some constants for simple numbers, including 0. Here I am setting the price to 0, and then I expect that the getter returns 0. And the same thing here, I'm setting the price to a new value. I expect that the getter returns the newly set price. And here in my third test, I have once again a lambda expression, and inside the method body of the anonymous method, it tells me the statement that should trigger the exception. In this case, if I call setGoldPrice with a negative number, even if it is quite small. Also notice that setGold is always called on the type. I was not using any of my private fields. At this point, please go to TreasureChest and implement the method setGoldPrice. Oh, one last thing I want to point out. The big decimal requires an import statement. So at this point, please go to TreasureChest and in TreasureChest, implement the method setGoldPrice. Pause the video. When you're done, press continue. Here is something to compare with. You might have noticed that the relational operators like greater or less than work with primitive types, integers, double, etc., but they don't work with big decimal. So if I want to compare big decimal, I need to use the interface method compareTo. So I'm comparing the gold price using the compareTo method with another big decimal, and the compareTo method returns either a positive value if gold price is bigger, or a negative value if gold price is less than 0, or 0 itself if gold price is equal to the value provided. In our case, we want to check whether this is negative. We want to check whether gold price is less than 0. So we need to ensure whatever compareTo returns is a negative number. If that is the case, we return the gold price can be negative, message for the user, and after that we are ensured that gold price has a valid value and we can assign it to the TreasureChest gold price. That is the static field. Notice I was qualifying the field. I could not use this dot. If I try this dot, it gives me a complaint because it is a static field. So I need to qualify it with the class name in order to distinguish it from my parameter with the same name. At this point, we are quite far. There is one more method that is left to do. The last method that we need to test is value in dollars. You can see the doc comment right here. It should calculate the dollar value of all the gold coins in the treasure chest. Now, if I look at the very top of my treasure chest class, it told me that in this treasure chest, every gold coin happens to be a $20 Liberty Gold coin. It also told me that the amount of gold per coin, per $20 Liberty Gold coin, is 0.9675 ounces. And in addition, it tells me that we have a current gold price. Now, given that information, try to implement the method value in dollars. Pause the video. When you're ready, press continue. Here is something to compare with. We can calculate the dollar value of the whole treasure chest if we know how much gold we have and we multiply all the gold with the gold price. Now, in order to find out how much gold do I have in my treasure chest, I need to multiply the number of gold coins with the amount of gold that is in each of the coins. Notice here I am using the multiply method, no operator, because the Java operators like plus, times, divided, etc. work for primitive types but not for big decimal. Also notice that I'm using chaining here, so when I multiply the number of gold coins with the amount of gold in each coin, that multiply method returns a big decimal, which in turn I can use to multiply again, this time with the gold price. I'm going to briefly open up the class BigDecimal in Java, and when I scroll down, you can see that there are some fields, for example 1, 10, 0. Those are simple numbers that exist already as a constant. There are some constructors, but you can also see the typical operations that we want to perform on numbers. For example, add, divide. When I scroll down a little bit further, we will find multiply. There's also subtract. Here it is. So we have the functionality, but it is provided as a method, not as an operator. You might have noticed that this time we wrote the method first and we haven't written any JUnit tests yet. I encourage you to write the JUnit tests first and then implement the methods, but sometimes we have reasons to do it otherwise. So if you have a finished method and you don't have the JUnit tests yet, that is not a problem. You can still add them. Please go to class TreasureChest test and add some JUnit tests for the method value in dollars. Give it a good try. Pause the video. When you're done, press continue. Now here is something to compare it with. Notice I started 2 test methods for value in dollars. One was testing with an empty treasure chest. So when my treasure chest is empty, I expect that the total value is 0. However, the second treasure chest was not empty. I wanted to test with my treasure chest that includes 10 gold coins. And there's one difficulty. How can I figure out the expected value? The expected value is the total amount of gold I have. So I'm going back to my treasure chest. I'm looking it up. I know I have 10 gold coins. I know each of my gold coins has 0.9675 ounces of gold. So far, so good. But then I also need to multiply the total amount of gold with the gold price. Let's look it up. So when I go to the gold price, I can notice we never initialize the private field. This is one of the reasons why JUnit tests are so important and so helpful. They can uncover bugs in the code that are not even within the one method we're trying to test. So here, if I look at my implementation, the multiplication seems quite reasonable. But when I need to identify what is the expected value, then all of a sudden I realize there is no expectation for the gold price unless somebody sets it. We're going to change this. We need to make a big decimal out of that. And now we have the information we need to predict the result. I can use a calculator or a browser to calculate the product. And here it is, 13,805.2575. We can use that as the expected value for our JUnit test. Let's run the tests. This time, not all tests passed. I still have the red bar. It tells me out of 20 tests, 2 failed. At the beginning of this video, we wrote tests, implemented methods, and everything worked right away. It is nice when that happens, but in a typical test environment, we also encounter situations where tests fail. Sometimes the cause is obvious and we can fix it quickly, but more often than not, it requires some problem solving. Let's find out why our tests fail. To do that, I'm going to click on one of those tests and I'm looking at the failure trace. It tells me the expected value and also the actual value. So I can, in order to see it better, I can right click and go to compare result. Here it shows me the expected value is 13,805 point something and the actual value is 0 e minus 52. That is a very, very small number, very close to 0 and very different from 13,805. Now we need to find out why is the value so different. One way to do that is to look at the 3 values that we used in our implementation. So when I scroll down in value in dollars, I can see we had one single line and we multiplied the gold per coin, and the gold price. What I would like to know is what are those 3 values at the time of execution. We could go in a debugger or we can also print those values. And when I run the tests again, it is providing me the typical output from JUnit, but in addition, we also get some output in our console window. And now I can see when I was running to test with the empty chest, we had no gold, we had the gold per coin 0.9675, etc. The gold price was 0. And the same thing in my with my treasure chest that included 10 coins. The gold price was 0. We just recently updated that. So here when I check my gold price, I can see we assigned a new big decimal. And yet at the time of execution it is 0. I want you to look in your code. Can you find why the gold price is 0? Pause the video. Give yourself a moment to figure it out. When you're ready, press continue. Let's remember when we wrote a test for the method setGoldPrice. When you look here, you can see the gold price is a static field. When I go to my tests and I scroll down to setGoldPrice right here, we assigned different values. In one of the tests, we assigned 1,376, and in a different test, we assigned 0. And when we assign a value to the static field, it changes it for all instances. And when we go back to our fixture, we can see that we created a new treasure chest with 10 gold coins and a new empty treasure chest every time before we executed the test. However, we did not change the static field. So once the test updated the gold price, it changed it for all methods that were executed afterwards. So we also need to make sure that the gold price is set back every time before we execute a test. I say TreasureChest, setGoldPrice, and we're going to use the same gold price that we used to initialize the field. At this point, let's run the tests again. The tests failed again. This time, the gold price is no longer 0. It is 1,426.90 and those additional digits. Something similar happened with the gold per coin, the 0.9675, and then all those additional digits. You might wonder where those extra digits are coming from, because we did not specify them. They result from the way floating point numbers are stored internally. Some numbers, like for example 1/10, just cannot be represented precisely as a floating point number. JUnit recognizes that in its overloaded methods of assert equals. Let's have a look at the class assertions. So here I can look at some of the overloaded methods of assert equals. You can see it is used to compare bytes or characters or double. Now in case of double, it provides an overloaded version that has a delta. Something similar is true for float. It provides the possibility to compare floats with a delta. Now let's see what this delta is doing. Here it tells us it asserts that the expected and actual values are equal within the given delta. It tells us how close do those numbers have to be that we consider them the same. JUnit provides overloaded methods that compare numbers of type double and float with a delta. However, it doesn't have such an overloaded method for BigDecimal. We have to write this functionality ourselves. Let's start by adding a field called delta. So here I'm going to add a private field. It is also final and it is of type BigDecimal because we are comparing BigDecimals. I'm capitalizing delta because concept-wise this is a constant, and this delta specifies the allowed level of imprecision. Let's do something fairly small, like 1/millionth, and then we need to make a big decimal out of it. At this point, we know how close two numbers have to be in order to be considered equal. Let's go to our JUnit tests. They're right here where we are comparing the value in dollars. Now, these, I no longer want to require that my expected value and my actual value are perfectly equal, but they have to be close enough, at least as close as the delta, in order to be considered equal. One way you could do that is the following. You could determine the difference between the expected and the actual value by subtracting one of the other and then using the absolute value to make sure we have a positive number. And then we use the compare to method in order to compare it with the delta. If the difference is less or equal to the delta, we're good. We consider it the same. However, if the difference is greater than the delta, then it is no longer considered the same. Before I ask you to update the tests, I want to show you one more thing. Let's go back to the assertions. So far, we always used assert equals to assert that the expected and the actual value are equal. There is also a method called assert true. This might come in handy when you update the test cases. So at this point, go back to your test class, update those two tests, pause the video. When you're done, press continue. Here is something to compare it with. I created a variable difference. It subtracts the actual value from the expected value, and then it calculates the absolute value. And once we have this difference as a positive number, we compare it with the delta. If the difference is greater than the delta, then the difference is too big and the expected and actual values are not considered equal. So we need to use the not operator. That means it can be equal, it can be less than, and as long as that is the case, the test should pass. At this point, I'm going to run the tests, and now they all pass. You can see the values still have all the digits, but it is okay. We are within a millionth, and that is close enough. At the very end, I want to bring up things to consider when writing JUnit tests one last time. There are a few more things I added, and I want you to keep that in mind. Identify different states you're testing for and choose test data deliberately. We did that. Also, use the feedback provided by the failure trace to help you figure out why a test failed. And last but not least, create a good habit of adding automated tests to your projects early on. This is it. It was a long exercise. I hope it helped you to increase your understanding of JUnit testing and to get started using them in your own projects. Have a great day.